Hi, Year 11. Okay, so this is going to go through the multiple choice questions for the heat transfer topic. So question 1 says, this diagram shows a fire. You can see the fire. Why does the smoke rise above the fire? Okay, and the correct answer here is C. The density of the air is lower at higher temperatures. So let's just make sure that we can get rid of A, B and D so that you're happy with this. So smoke evaporates more quickly at higher temperature. Well, that's really got nothing to do with rising. And also smoke is actually a solid particle and it hovers on air. So if we think about the smoke, it's like little bits of black dust, as it were. Okay, now it's floating around in the air. That's not going to evaporate from being smoke, okay, because smoke is solid. Solid to liquid or solid to gas is not evaporation. Okay, evaporation is liquid to gas, so it's not A, so we can get rid of this one. Okay, now a lot of people chose B. Now the word diffuse, which you can see here, is really a term that we mostly use in biology. Okay, so diffusion is something that you often look at in biology, and we're not looking at diffusion. Okay, so we're not looking at smoke molecules crossing a barrier here. We are looking at density changes because we have a convection current. Okay, now we know that the smoke is rising basically because the flames here are taking the air particles and making them vibrate more. Okay, and if they vibrate more, they expand and take up a bigger amount of space and they start to spread out. Okay, so they look more like the top ones. Okay, now if you have particles that are really spread out, they are less dense than particles that are really close together. Okay, sorry about the shadows. This makes them more dense. Okay, now the density of air is less at higher temperatures. Okay, so close to the flame and close to the wood, we get the air heating up and becoming less dense. They vibrate more and take up more space. Okay, so that makes them less dense and there's more dense over the top. Okay, now we know that more dense sinks and less dense rises. Okay, so that is how the smoke rises, because the less dense air carries the smoke up. Okay, so that's number 1. Here's number 2. We've got a beaker of water at room temperature, point X, point Y. How could a convection current be set up in the water? Lots of people choosing stirring. Okay, now I know that when you think about the ocean, a current is where you've got movement of water, so that might be why you've chosen C or D. But the key here is that it uses the word convection in the question. Okay, so we know this is heat transfer in a fluid. Okay, that's what we mean by convection. So we have to have energy being moved from one place to the other if we have a convection current. Okay, so we have to have a difference in temperature. So we know that colder water is more dense. So cold is more dense, and hot or hotter is less dense. Okay, now the only options are cooling, and we know that if we make something colder, we make it more dense. Okay, and if it's colder and more dense, it will sink. Okay, that's important to think about. So in deciding where you cool it down, if we were to cool Y down, there's nowhere for the water to sink. It's already at the bottom. So instead, we cool X down, maybe we put some ice here and cool it down. The cold water at the top is more dense than the room temperature water down here, and it sinks and pushes the room temperature water up. Okay, and that will set up a convection current, so that gives us A. Okay, number 3, sorry if that was noisy. Again, we've got a fire. Which waves carry the most heat to her hands, and are they electromagnetic? This is just a basic memory one. Okay, now we know that a fire does emit visible light, okay, but visible light isn't really the wave that gives us the most energy as heat. Okay, that's infrared. So it's definitely A or B. And then you just have to remember that infrared is part of the electromagnetic spectrum, okay, where we've got a big range of wavelengths going from, I'm not doing a very good drawing here, but you get the idea, from very long wavelengths to very short wavelength. This is going to be our next topic, but infrared is part of the electromagnetic spectrum, so it's a yes. Okay, number 4 then. Hot liquid in a vacuum flask cools extremely slowly. This becomes because some methods of heat transfer cannot take place in a vacuum. Okay, the key word here is a vacuum. Now what we mean by this is empty space with no particles. Okay, so there are no particles in a vacuum. Now, conduction is where we have heat transfer in solids because of particle vibration. Okay, so remember, this one starts to vibrate more and it collides with this one and it transfers some energy over to this one. This one starts to collide some more, it transfers some energy onto the next one. Well, we need particles for conduction to happen. So we know that conduction cannot take place in a vacuum. Okay, so we can get rid of any that don't talk about conduction because we know that conduction cannot take place. Okay, so we're going to get rid of C because it doesn't even refer to conduction. Okay, convection we were just talking about. Okay, it's to do with the particle density. Okay, so remember that if we've got particles that are less dense, they rise, and particles that are more dense, so closer together, sink. Okay, and that's how we get this convection current set up. And again, this clearly needs particles. So convection needs particles. Okay, so therefore, I know that a vacuum cannot have convection happening in. Okay, but radiation in the other two, we know can happen in a vacuum. That's how the sun delivers energy to us. Okay, so if this is the sun over here, and here's Earth, this space in the solar system is a vacuum. Okay, there are no particles there, but the sun still transfers energy to us. We warm up because of the sun. So we know that we can't choose ones that say radiation because the question is asking whether it cannot take place, and we know that it can. Okay, so it's only conduction and convection that cannot take place. Okay, here we go. We've got a box, and inside the box we place a candle on the left, and we've got an open air chimney here on the left and also one on the right. And it says we light the candle, we hold a smoking taper. All that means is a piece of paper that gets lit on fire and then blown out so that it is smoking. Okay, so it is emitting lots of smoke. Okay, just like if you had an incense stick or horribly a cigarette. Okay, when you, or a match, if you light it then blow it out, you get smoke given off. Okay, and then it says, in which direction does the convection current cause the smoke to move? Okay, so we're looking at a convection current. We know that that is set up because of a heat source. The heat source is the candle. Okay, so the particles by the candle start to vibrate more. Okay, they become less dense. Okay, we know that heat makes particles less dense, so they will rise. Okay, so they move up out of the chimney. Okay, so particles that were inside the box now leave and are up here. That leaves empty space inside the box where the particles were. Okay, so we've got a very empty box that doesn't have particles in anymore, so very low density. Okay, but outside the box, up here, we've got normal air. Okay, now this cool normal air is more dense than the empty space, and it sinks into the box. Okay, so the convection current is set up and it goes round and round in this direction. I'll give you a link to a YouTube video that shows this experiment happening so you can see it. Okay, number 6. We've got a piece of wood with some iron nails pushed through it. One side of the wood is covered with heat-sensitive paper, which turns from pink to blue when heated. Okay, the wood is heated for a few minutes and blue dots appear on the heat-sensitive paper where it touches the nail. Okay, so I'm just reaching across to get some colours. So, this is where we see the blue, which means that the rest is left pink because it starts pink. Okay. Now, the heat source is over here. We send the heat in on this side. Okay. The heat starts on the left. It has to get to the right in order to reach the paper because that's over here. Okay. So we know that there has to be heat travelling from left to right. Okay, so energy is going from left to right. We get an energy transfer. Okay, now we know that it has to transfer through whatever we have inside. Now, all of this is wood. Okay, so most of the heat is travelling through wood. Okay, but there is a point where the nail is inside the wood. Okay, so heat that's applied here is going to travel through the nail instead. Okay, and what we see is that the heat reaches where the iron nails were much quicker than the wood, okay, because it was only where the nails were that went blue. Okay, so remember, this is about energy transfer. So this is about thinking about how we transfer energy. The only two options for heat transfer are B and C. Okay, so we can cross out A and D because we're not looking about absorbing or emitting. We're looking about energy starting in one place and needing to get to the other side. Okay, and because it's physically touching and because it's a solid, we know that solids transfer energy with conduction, so we choose B. Okay, 7. We've got a cool box which uses 2 ice packs to keep it cool. So this is what you take when you go on a picnic and you go outside. If you imagine, it looks a bit like this. Here's your box. It would normally have a lid, but don't worry about that for now. The food's all at the bottom. I'm not going to draw food because I'm not that good at art, but imagine your food's here. You put it in. The question is asking, where do you want to put your ice packs? Do you want to put the ice packs underneath the food, or do you want to lay them on top? Okay, now ice packs are cold. Okay, the food is warmer than the ice packs. Okay, remember that cold air sinks and hot air rises. Okay, we know that from convection. If we have cold ice packs, we know that the air next to them will sink. Okay, so if we were to place the ice packs underneath the food, the ice packs would make the air cold, but it would sink down. Okay, and so all of the food that's up here wouldn't get any of that cold air, and that's not going to help keep the food cold. Okay, whereas if we take the ice packs and we place them up here, their cold air sinks and goes through the food. Okay, and when it goes through the food, that will keep the food cool. So we put the ice packs at the top. Almost there. Dearie me. Okay, similar question here. This time, instead of it being a cool box, we've got a refrigerator. Okay, we place the cooling unit, so this thing is cooling the fridge down, at the top, because we know that the cold air next to it is more dense and it will sink, and the warm air at the bottom will rise. Okay, so if we kind of colour it in to represent the hot and the cold, the air here at the top by the cooling unit is blue. It's more dense. Okay, the air underneath, which absorbs the heat from the food, is warmer. Okay, so it's less dense air here. And so this more dense air will sink, and the warmer air from the food that needs to be cooled down moves up to the top. Okay, so now this cool air is going to replace the warm air and cool it down. So that gives us A. Okay, number 9. 2 plastic cups are placed inside one another. Hot water is poured into the inside cup and a lid is put on the top. Which statement is correct? Heat loss by radiation is prevented by the small air gap. That is not true, okay? Radiation can travel through air. Okay, radiation can travel through air. Let me send that up a bit. So that's not going to prevent radiation, so that's not right. No heat passes through the sides of either cup. Not true, okay? There'll be a little bit of conduction through the walls of the first cup. There will be convection inside the air. There'll be some heat transfer that way. And there will be radiation being given out from all sides. Okay, so that's not true either. The bench is heated by convection from the bottom of the cup. Now remember that if we have a convection current, the hot air rises and the cold air falls. Okay, so the heat moves upwards. So we're not going to heat the bench down here because the heat doesn't travel down that way through convection. It travels in the opposite direction in convection. Okay, the bench does get a bit hotter when we place a hot cup on it, but that's from conduction. That's because particles at the bottom are vibrating lots and they come into contact with some of the particles in the bench. Okay, and it happens via conduction, so that's not right either. Last one then. A boy sits near a campfire. He pokes the fire with an iron bar. We know that that is a conductor of heat. Okay, his hand becomes hot. In which ways does thermal energy from the fire reach his hand? Well, firstly, we know that iron is a conductor, so we can tick conduction. We know that that is going to help us, so we can get rid of C because it doesn't even mention conduction. Okay, next we have to choose between convection and radiation, or just conduction and radiation. Now remember, the heat in convection rises. Okay, so the hot air rises in a convection current, it goes up. Well, the boy isn't up here, he's over to the side. Hot air does not go to the side because of convection. Okay, so we do not have convection helping us get heat to the boy. Okay, so we can get rid of A and we can get rid of D. Conduction happens through the iron bar. And radiation happens in all directions, always. Okay, so that will always go everywhere. To the boy, also to over here.